Okay, good afternoon, everyone. Let me go ahead and welcome you to the 11th week of the Frontier Seminar Series. It has been a privilege to get this thing started, and I'll take a minute and just thank our organizing committee for working with all the junior faculty members and nominating them and identifying moderator for this series. So before we go on the proceeding for this week, let me give out just for the next week. It's not going to be on the Thanksgiving. So we're going to have our week 12 seminar on December 4th. The theme for that week is bioengineering. And we have two outstanding speakers from University of Wisconsin-Madison, Professor Corinne Henach and Professor Neil Lin, who is also on the organizing committee from UCLA. It will be moderated by Ellen Aruda, Department Chair, School of Mechanical Engineering at University of Michigan. With that, let me just go ahead and start the proceeding for today. Our theme is system reliability and control. We have two speakers, emerging leaders in this area, Professor Katrina Groth from University of Maryland and Professor Neera Jain from Purdue University. And Mark will do the formal introduction, but let me just go ahead and introduce our speaker. It's a great privilege for me to introduce my mentor in some way, Professor Mark Costello, who is a school chair for School of Aerospace Engineering. And Mark is really somebody, when I was thinking about who to bring on this show, he's a person who has engaged in mentoring junior faculty. So it's a great person to have on this series and share his vision about the system and try to introduce the two people. Mark, before he was school chair, he was program manager at DARPA for 2 years. And he is a homegrown leader, is what we call at Georgia Tech. He has done his PhD at Georgia Tech. He has been a leader here. And Mark is double jacket even for the kids. I think everyone in his family is bleeding Georgia Tech blood. So it's great in that area. He is greatly known for his work in the area of guidance, navigation, control, and systems engineering. He's a fellow of ASME and AIAA Associate Fellow. And there's a lot of different awards Mark has won. Without going into too much detail, I'll give the floor to Mark. It's an honor to have you as moderating this session. And thank you, Mark. The floor is all yours.
Great. Thanks, Devesh. Well, the honor is all mine to be here, really. Today we have two superb scholars with us that are going to talk on systems reliability and control. So let me first introduce Katrina. So Katrina is an assistant professor in the Department of Mechanical Engineering at the University of Maryland. She's the associate director for research at the University of Maryland's Center for Risk and Reliability. And she also directs the Systems Risk and Reliability Analysis Lab. She's a worldwide expert in the area of systems risk and reliability analysis and has had a particular focus on hydrogen safety systems. Before Professor Groth joined the University of Maryland, she served as a principal R&D engineer at Sandia National Labs. She holds a bachelor's degree in nuclear engineering and MS and PhD degrees in reliability engineering, and they're all from the University of Maryland. With that, let me now introduce our second speaker, Neera Jain. Professor Jain's an assistant professor in the Department of Mechanical Engineering at Purdue University, and she's an expert in the area of dynamics, controls, optimization, and thermodynamics. She had been a visiting summer researcher at AFRL and was a visiting member of the research staff in the mechatronics group at Mitsubishi Electric Research Laboratory. And interestingly, she's been a contributor to Forbes on the topic of human interaction with automation and its importance in society. Professor Jain earned her MS and PhD degrees in mechanical engineering from the University of Illinois and her SB degree from MIT. So with that, I'd like to turn the floor over to Professor Groth. It's all yours. We're looking forward to hearing your talk.
Great. Thank you very much, Mark. It's really exciting to be here today, I guess virtually, and to connect with this community on my research and how it connects to the broader field of mechanical engineering. So today I'm going to talk about exploring the intersection between risk assessment and prognostics and health monitoring in the context of complex engineering systems. So before I start, I figured I'd talk a little bit about who I am and what do I study. And given that mechanical engineering is so broad, I think it's important to talk about what is reliability engineering and where does it fit into mechanical engineering and where we're going. And then I'll talk about my research, but where we're really going is that I want you to understand that there's a lot of interesting opportunities exploring the intersection between PRA and PHM so that we advance reliability engineering in our modern era, where we're really thinking about complex systems, big problems, and digital transformation. So if you leave this presentation with one impression, I want you to understand that there's this vast opportunity to change the way that we do reliability engineering to solve the next generation's problems. So Mark mentioned my background pretty briefly, but just kind of a quick snapshot of where I am and what I've worked on. So my engineering research it really falls at the intersection of energy technologies, complex systems, and risk and reliability. So I've worked on nuclear power plants, which if you're in the nuclear world, you'll see it talked about as probabilistic risk assessment. And the goal is to inform regulatory applications through new PRA methods and through causal models of human reliability analysis. In hydrogen world, I've worked on safety codes and standards for fuel cell infrastructure. So unlike nuclear power plants, hydrogen systems are regulated by codes and standards instead of a federal regulatory authority. And in my work, I've used quantitative risk assessment, the oil and gas framing, QRA, to create some safety standards for technologies that are brand new. So some of this work has resulted in a new computing software called HIRAM and been used to develop ISO 19880-1, which is the international standard that is a consensus-based standard for how we do hydrogen fueling safety. And then the third aspect of where my work is relevant is oil and gas. So in this world, it's called pipeline integrity management. And I've been working on both the prognostics methods for predicting and managing pitting corrosion in pipelines, and also predictive methods that can help prioritize and identify root causes of third-party damage during pipeline excavation near pipelines. So in 2017, I came to UMD as faculty to establish my lab, which is SIRA. In essence, we're working on a combination of basic and applied research in the realm of risk assessment for complex systems. So a big question is always, what do you consider a complex system? And I'm looking at this as humans and machines and environments and physical phenomena. So it's really a large-scale system, and a lot of the work that I do is informed by models and engineering and data. So we do a lot of data analytics and machine learning, but it's not just that. We have to combine that with engineering expertise and models for bigger problems. So we're pulling all of these modeling and data frameworks together, ultimately to help make better, safer energy systems. So I wanted to both thank and acknowledge the students that I have in my lab right now. And again, we have a lot of active research going on. And in 2021, I do anticipate having an open position for a postdoc and a PhD student, focusing on computing and software for PRA and focusing on human reliability for natural hazards in nuclear power plants. So if there are any interested candidates online, please reach out and contact me so that I know to alert you when those positions are posted. So why do we study risk and reliability? I think as engineers, we take for granted that our systems are important, but they really are. I think, we're a little bit behind the scenes, but engineering systems, the complex systems that we build, are at the core of the US economy, the security, and the quality of life that we have. So power plants, pipelines, aircraft and defense, all of these systems are underpinning what we think of as a modern society. And as engineers, we know that these technologies are transformative. But engineering doesn't stop when the product is delivered or when the lights come on. And one of the things that's really important is that we know that systems can be engineered for safety and reliability. So safety and reliability are not side effects, they're something that we engineer. And it's really important that we as engineers have insight into how to prevent and mitigate and recover from system failures and accidents. Because if we don't, we have these catastrophic failures that both cause significant loss of life and potential environmental damage, but also even loss of trust in the systems that we're creating. So it's a really important aspect of mechanical engineering that is a little bit behind the scenes is this safety and reliability world. Risk assessment itself has been well established in these so-called high consequence industries for decades. So even in the 1950s and 60s, we were building statistically based models using exponential and other distributions with time to failure data. As we progress in our modernization of the techniques, we started understanding more about accelerated life testing and maximum likelihood estimation. Right about the 90s, there started being more consideration of physics of failure in our probabilistic methods. So not just looking at statistics, but connecting that to cause and effect models. And in the 2000s, that blossomed into more hybrid modeling approaches using both deterministic and probabilistic models along with Bayesian approaches. So in the 2010s and in the future, we're seeing a lot more consideration of prognostics, of system health management, these causal models, and of course the big data, but also sparse data. We want to use all of the information we have, not just the big data. And as our reliability techniques scale up, we are also considering more about complex systems or even systems of systems, and really trying to grapple with how we continue to solve problems at that scale. So this digital transformation is motivating completely new questions for risk assessment. And earlier this year, ASME President Richard Loudonaut gave an opening speech at a virtual seminar we had at UMD. And he indicated that this digital transformation is a revolution. And part of that is that we have to think about fundamentally new ways to think about and work with the technologies that we've been using for so many years. And so within this reliability and risk world, we have so much more data, so many more algorithms, and they're in so many more formats and scales than we ever imagined. And so within this, the big questions become, how do we actually use this to make the system safer? But we have to make sure that that question is also connected to a second question, which is, we don't want to turn risk assessment into a black box that just churns out the right quote unquote number for safety. We also don't want it into a crank that we need to turn, because we want to get good data informed insights, but we have to have engineers who connected into knowing this so that we can actually fix the problems. So we have to kind of balance this data world, but also make sure we still understand things. So there's two facets of reliability engineering that I've already touched on, the PRA and the PHM. And while they're both within the same field, they're relatively siloed. So when I talk about PRA, what PRA is it uses systems engineering and reliability engineering methods. And the goal is to identify system failure scenarios and estimate the probability of events and scenarios that lead to certain consequences that PRA helps define. So this is a really well-established body of techniques in the high consequence industries. We blend data and models and knowledge and help support this decision-making process. But the downsides of PRA is that it's mostly kind of an offline type of analysis, and it's updated maybe annually, maybe less. It really depends on the industry that you're working in. On the PHM side, this is our data-driven side. This is coming from the computer science methods, the new machine learning and AI. We're using online monitoring or sensor data, data pre-processing, feature extraction techniques, so that we can perform health state assessment or fault diagnostics, and ultimately to predict the remaining useful life of something of interest to engineering. So PHM is great at online data handling and decision support in near real time. But the big challenge of PHM is that it happens at this component level or dealing with very simple systems. And there are really big questions about how we could scale this up to address not just a more complicated system, but a system where we have a whole lot of uncertainty, missing data, and a lot of interdependencies. And a lot of the research that's happening in both of these fields are completely siloed. So PRA and PHM are independently looking at algorithms and at data analysis methods. We're expanding the hazards and tools that we're dealing with. But in recent work in my lab, we found, and we were surprised to find, that in all of the main engineering journals in our field, that there were only a handful of articles that fell at the intersection of both of these two techniques with respect to a complex system. And this got us thinking that we really need to embody, the benefits, the pros of both of these techniques. But the first step to get there is that we have to really think about how do we build a unifying framework for connecting the pros and the good data and algorithms from PHM into the PRA models that have been proven for supporting decisions in complex engineering systems. So on this work, the objective was then to develop that unifying conceptual and mathematical framework that connects the PHM data and algorithms to PRA. And what we're really trying to do is find that sweet spot over here where we're taking this data complexity and predictiveness capabilities from PHM and the system complexity and model depth and richness from PRA to provide something that is causally aware, but also operationally aware and responsive to provide system level rapid health assessments. And so on this slide, I've kind of framed out some of the first steps that we took, and this is, again, it's going to be published. It's in the published article, so you don't have to squint necessarily to see it. But in PRA, you see there's several key aspects of PRA that are not included in PHM. So you see there's this objective and scope setting activity right at the start, and some information assembly and consideration of the initiating events and the hazard scenarios. So a lot of effort in PRA is on this front end of developing the understanding and the data sources and assembling data so that you can build these detailed scenarios that help you understand how combinations of events lead to certain outcomes in your system. Which, again, we're usually focused on preventing failure, but we never just want to model failures. We're also modeling how barriers come into it and prevent scenarios from resulting in failure. And on the right-hand side of PRA, of course, we build these into the logic models that are the most recognizable aspects of PRA. And we, of course, connect those to models of consequences. And then we assess our results in terms of things like total risk and probabilities, importance ranking, and of course, we must also consider uncertainties. When we think about PHM, it starts completely differently. It starts with a system, which is usually just the machine. And it starts with sensor data that comes straight out of that system. So we're not collecting a spectrum of data to provide a whole system context. We're collecting just the data we have in a sensor-based format. And we're using that in these diagnostics models to do condition monitoring, anomaly detection, and ultimately isolate and identify the false and the failure modes of that particular simple component or simple system. And then with that, we also use prognostics models to predict out the time to failure of that particular system and understand how its failures can progress. And the decisions are almost always focused just on managing the health of that particular system or component. So what we've done is pulled these together into a conceptual framework, and you'll see hints of each of the elements, but you'll see there's two aspects involved. There's a framework construction phase and a framework application phase. And so within this framework, the first step is very informed by PRA. We need to figure out what the objectives are, whether it tends not just to be fix one piece of equipment. It tends to be much more along the lines of supporting a decision where you have a whole lot of pieces of equipment. You have humans, you have this complex system, and you have some sensors, but you're monitoring this overall process. And so this is informed by not just our sensor data, but also by our historical data and system description and system models that we see in PRA. So the subsystem level analysis comes from what the PHM looks like now. That's our machine learning based model training and development to build diagnostics and prognostics models at a component or subsystem level. And we connect that into a PRA framework, which is the system level analysis. And ultimately, we'll have this dynamic framework created that we can then use going forward to solve and support decisions about that system. So on the application side, that's when the user side of the framework starts, which is that we're now collecting the real-time data on the system as if we were in a PHM process and doing all that data manipulation through our standard algorithms. And you'll notice that there's both a system level diagnostics and prognostics that happens and a subsystem level. So we need to be able to have an understanding of those subsystem failures and prognostics, but we connected that to a system logic model so that we can now understand at the system level how those subsystem diagnostics and prognostics translate into system health and risk. And ultimately, we're able to support the types of decisions that were framed out during our objective selection. So recently, we implemented this on a case study of a simple system. And the goal was to start with a simple system before we tried to scale it up to a real complex engineering system so that we weren't tackling too much at the same time. But we started with just a simple system, which had 5 components. It's a mining stone crusher system. And we had 14 sensors, a year of operational data with 14 sensors where we were getting about 30 samples per hour. So we had about 250,000 data points from this operational second by second sensors. And we also had a year of maintenance logs. And these maintenance logs were text-based. We had 37 events where there was downtime, and they spanned about 900 hours of downtime for various reasons due to failures in combination of these components. So what we did was we developed this algorithm using the framework we outlined before, and combined the PHM results from these 5 components, each of which was a subsystem model developed with a different deep learning method, and connected that into a fault tree representation of the system's failure logic. And we were pleased with the results. So the results initially show that the method is viable, flexible, and fast. So for this simple system, we were able to, after we parameterized it, we were able to run it in sub-second times on standard desktop computing computers. So the method is flexible and fast. And we were very pleased to see that the component results showed good performance and accuracy. So the top right chart is those component results, and you'll see that we're getting very high true positive rates and low false positive rates for 4 of the 5 components. The filter was actually a little bit of an anomaly with the true positive and false negative rates are not very good. And we determined that's because we only had 1 sensor for that filter. So that's one area that we need to consider for further improvement in just the subsystem model training. And again, these results were we used different deep learning algorithms for each component matched with its data type. And the performance that we're seeing here is very consistent with what we would expect from those algorithms given the data characteristics we had. And then that second chart on the right, you'll see our system monitor. And we are able to show that we were actually able to get the system level online monitoring capability, and that we are able to predict the times that the system would be abnormal based on the component data and that system structure. And so in the bottom, you'll see our initial system results. We're seeing 83% true positives, which shows that there's a lot of potential for the method. And we understand, of course, that the false negative rate is higher than we would like it to be, and that we need to do additional work to refine algorithms for this particular system. But we're pleased to have this performance baseline. So we know it's possible and it's computationally tractable for a real system. And now we have a baseline for comparing how our improvements work and if we can scale this up to a complex engineering system. So the next steps are where we're going to start getting into the complex engineering system. And we're designing and implementing the algorithm on a 2-stage vapor recovery unit, which has 7 main subsystems and involves human interaction with the system. So we have a motor and compressors and heat exchangers. So we have our 7 main subsystems plus their integrated components, and we have data from 188 different sensors that have various sampling rates spanning a wide variety of sampled variables for each of those components. And we have 72 recorded system failures for this system. So this is work in progress. I don't have an exciting result that's going to say, yes, it definitely worked, it's great, and our true positive rate is 98%. But the scenario development and the modeling is on track. We've been able to apply our standard PRA techniques, looking at scenario development through FMEAs and HAZOPs, building event trees and fault trees for this system, and ultimately translating aspects of that system reliability model into a Bayesian network model that also connects into the PHM monitoring nodes. So we've connected all of these pieces from these 2 disparate parts of the field. And so far we've been able to produce results that are rapid. And again, the computational time is still sub-second for the predictive capabilities, and is able to differentiate between healthy and degraded outputs for that system. And this model is still in development, but stay tuned. We should have interesting results in the next year or so. So before we wrap up, I wanted to talk about another next step, which is a workshop. So I mentioned that workshop, we had an online virtual workshop at the beginning of this calendar year, which was actually intended to be an in-person workshop that we're calling PACES, so a PHM approach for complex engineering systems. Of course, 2020 happened and the workshop has been postponed, but we are intending to have it in 2021 in person when it's safe to have people travel and get together again. The pre-workshop results are available online, and we would definitely welcome more participation from the academic community so that we can have hopefully some really exciting and interesting in-person discussions about where this goes, how it connects to application problems, and are there broader case studies that we can use to pilot this algorithm and to vet this algorithm on those applications. So my last slide is the impact. So right now we're connecting these 2 aspects of reliability engineering so that we can look at new ways of diagnosing, understanding, and mitigating failure. We're enhancing PHM alone by introducing this holistic system level approach that really embraces engineering knowledge with the data. And on the PRA side, we're enhancing PRA by providing guidance on how we incorporate this new machine learning and data science modeling world to provide more adaptiveness and predictiveness in PRA. And I think one of the additional impacts is that we're really improving this cross communication between these 2 siloed facets of our field by creating this bigger framework that can solve problems that we could not solve alone. So with that, I will thank you for your attention. And again, I will welcome questions in the chat, and I will turn it back over to Mark so that our second speaker can provide her perspective. Thank you.
Great, that was terrific, Katrina. Thank you very much. Really thoughtful presentation. Okay, so our next speaker, Neera, are you ready to go?
I am. I am going to go ahead and start screen sharing here.
The floor is yours.
All right, let's do. Can you see my PowerPoint?
Yep.
Okay, great. Well, thanks again, Katrina, for that excellent talk. And actually, as you were presenting, I was thinking about a lot of the similarities between my work, and I might touch on some of those as I speak. And thanks again for the opportunity, Georgia Tech, for participating in this seminar series, which I think has been a really neat opportunity especially for assistant professors. So the title of my talk today is Enabling Human-Aware Automation, a Dynamical Systems Perspective on Human Cognition. And so I'm going to focus on sharing some of what we've been doing in my lab over the last several years in this area of how humans interact with automation. So I think that everyone can probably agree and identify with the fact that as humans, we are increasingly interacting with automation. But despite all the technological advancement that we've seen in the development of automation, autonomy, and robots, what we find is that the outcome still falls short of our intentions or expectations for that technology. And what I'm showing here is an image from a hospital in Italy taken earlier on in the pandemic. And on the right is a quote from the hospital's ICU director who said, "You have to explain to the patient the aim and function of the robot." And I meant to mention that there's these nurse robots that were deployed in this hospital, because the first reaction is not positive, especially for old patients. So here's an example where these, I think from a technology, from an engineering perspective, we would say some really innovative robots were designed and deployed with the goal, of course, of helping nurses and doctors to interact with patients, help human doctors and nurses to keep distance from the patients who are very sick, help alleviate the load on those doctors and nurses when maybe more simple tasks needed to be accomplished by these robots. But if you put yourself in the position of the patient who is sick, probably scared, in an uncomfortable environment, I think we can all imagine that the last thing we really want when we want to see a human doctor or nurse is to have this robot roll in and ask us questions. And so really the question that motivates us is, how do we actually better design automation to interact with humans in a way that is more natural, really? And we know that there are several cognitive factors that affect how humans interact with automation. And this has come from decades of research, largely in the human factors community. There have been several conceptual frameworks that have been developed that capture these complex interactions between, again, what I'm calling cognitive factors. And I'm showing one such diagram here on the left, and I've highlighted a couple of words in yellow that are I'm going to be using in today's talk. So for example, we see that a human's trust in the automation directly affects their reliance on or choice to use that automation. The machine's accuracy or reliability affects that trust. And things like the human's workload or other things like their perception of risk or their fatigue will also affect how they choose to rely on that automation. So these conceptual frameworks are extremely valuable to us. But then the next question is, well, from the perspective of as a controls engineer designing automation, how do I translate this type of understanding or knowledge into something quantitative that I could maybe use in real time? And there haven't been several quantitative models that have been developed to predict things like changes in trust and changes in workload, because both of those have been shown to be dynamic quantities. However, there are still two important gaps that have motivated the work that I've been doing in my group. And so the first one is that we haven't seen as much modeling that specifically looks at mapping automation outputs to these cognitive factors. So in other words, we need a model or a relationship between what the automation can actually control and how that affects the human's decision to interact with that automation. And then we also, based on those models, need control policies then that can help us to achieve what's called adaptive automation. And we're specifically interested in adaptive automation to the human's cognitive states. Oh, there we go. So to give you a quick overview of my research program in this area, before I jump in to some specific work today, we've been doing a lot in the space of control-oriented model development for human cognitive behavior with a focus on estimation and prediction of human trust and workload, also considering things like demographic factors and how those impact trust evolution. And more recently, we're looking at how human trust can evolve on multiple timescales. We've also considered psychophysiological-based estimation of human trust. So how do we use psychophysiological data in addition to the behavioral data that we can collect from humans to understand human cognitive behavior? And then again, how does that impact our ability to design better automation? And then what I'm going to be focusing on today, in addition to the modeling, is how we've used those models and actually closed the loop between human and automation. So we've designed control policies that enable us to realize a form of adaptive automation. And I want to, before I then jump into this, acknowledge a couple folks, my collaborator at Purdue, Professor Tahira Reed-Smith, who's an associate professor in ME, has been doing this work with me for the last several years and is really the expert on psychophysiological sensing and human subject experiment design. A former PhD student, Dr. Kumar Akash, who's now a scientist at Honda Research Institute, who really was the lead student on all of this research, and then an undergrad who contributed heavily to the work that I'm going to share today as well, Griffin McMahon, and then several other former and current students who are working in this area. So today, what I'm going to do in our limited amount of time is focus on the following. I'm going to describe automation transparency and why for us it's an important control variable in this problem. I'm going to talk about the probabilistic modeling framework that we've developed for estimating trust and workload. I'm going to talk about the human subjects experiment that we've designed and implemented to collect data for training that model. And then, as I mentioned, share with you the control, the closed loop policy that we developed in its implementation, and then wrap up. So automation transparency is a very valuable control input for us, or control variable from our perspective, because of how it affects critical human cognitive states. So transparency, there are a few different definitions. The one that we use is the following: is a descriptive quality of an interface to afford an operator's comprehension about an intelligent agent's intent, performance, future plans, and reasoning process. And so the emphasis here is on these bold words. And it's useful to think about transparency in the context of different levels of automation. And when I say levels of automation here, I'm not referring to the SAE levels of automation that people are very familiar with because of self-driving cars, but actually a more general definition of levels of automation that was first presented by Parsurman. And so the lowest level of automation is really what we call acquisition automation. And as it suggests, this is automation that simply is collecting information for humans. The next highest level of automation would be analysis automation, where the automation takes that information it's collected and processes or analyzes it in some way. The next level would be decision automation, where based on that analysis, it makes a decision or recommendation to the human. And then the highest level of automation, which I don't show here, would be action automation, where the automation actually has the control authority to act on the decision or recommendation that it's made. I'm going to be stopping here at level 3, and this is sometimes called, decision automation is sometimes called intelligent decision aids. And a good example to sort of anchor this in, it would be Google Maps. So for example, if you've used a navigation map before, it's giving you turn-by-turn directions, but ultimately it's up to you as to whether or not you comply with those instructions or not. Google Maps doesn't actually have any authority to drive your vehicle for you. And so given these different levels of automation, we can think about transparency in the reverse direction. So what do I mean by that? The lowest form of transparency that automation could use to communicate back to a human would be by just communicating this decision or recommendation that it's made. A medium level of transparency, in which, in addition to providing that recommendation, it shares some amount of analysis that was done to reach that decision. And then the highest level of transparency would be one in which even some of the raw information that was used to do that analysis is also shared with the human. And what's great, as I mentioned, is that it's been shown that transparency does indeed affect critical human cognitive states like trust and workload that we then know actually affect human decision-making when it comes to interactions with automation. Increases in transparency typically lead to increases in trust, which in turn typically lead to increases in compliance. Similarly, or I should say that transparency, or an increase in transparency, can also lead to increases in workload, which we can observe as increases in the human's response time. Now, if we think about how can we take these relationships and actually model them in a quantitative way, it's important to recognize the following. The first is that trust and workload are really hidden states. These are things that we can't directly measure or observe from the human, but that are important for us to understand because we know that they, again, affect that decision-making of the human. What we can observe are the human's compliance and their response time. And we also know that these trust and workload, these cognitive factors that I'm going to start calling cognitive states, are also affected by other factors like system reliability and the context of a given situation. So given the fact that I really need to estimate these states, a natural framework for us to use is a partially observable Markov decision process, or a POMDP. And what a POMDP is a 7-tuple that consists of states, actions, and for those familiar with a deterministic state-space representation for modeling a dynamic system, the actions really are analogous to inputs. There are a set of observations, which are really outputs that we can measure. And then the state dynamics are governed by transition probability functions as well as emission probability functions. And another useful thing about this framework is that we can use it to design optimal control policies. So the same way that I could define a cost function and minimize it to design an optimal controller, I can pose a reward maximization problem here, where I determine the optimal actions needed to maximize my reward. So we can take a POMDP and define actions, states, and observations that give us the ability to model human cognitive dynamics. So we can model the states here as trust and workload, and our observations, as I described earlier, as compliance and response time. And then we define 3 different actions, which again are really the inputs that affect those state dynamics. So one, of course, is transparency. That's again, the sort of our control input. That's what the automation can actually control as it interacts with the human. And there's 2 others that I've added. One is the recommendation that's actually made by the automation. And very generally, we can define this as the absence or presence of a stimulus. So if this was a health detection system, the stimulus might be the absence or presence of disease, for example. And we also define as an input the human's experience with the automation. And what this really is whether the recommendation made at the previous trial was a faulty or reliable one. And that we know affects the human's trust. And so at this point, I've defined this POMDP, but it's still general enough that I've not specified a particular human machine interaction context. It is somewhat specific to intelligent decision aids, but that's still pretty general. And one thing that we have done is apply this to multiple contexts to show that it is more generally applicable. But the specific context that we use to actually then train this model specifically to identify those transition and emission probability functions is a reconnaissance mission study. So we designed this experiment where the objective of each participant was to surveil several buildings with the assistance of a virtual robot, and to do that in minimal time. And so the participant would interact, again, with this virtual robot that was 70% reliable. And we didn't tell the participant exactly what that reliability was, but it's important to know that the robot didn't always make the right or correct recommendation. And the human each participant completed 3 missions with 15 buildings each. And what's important is that in each mission, they interacted with a robot that used a different level of transparency. And so by doing this, we were able to collect a lot of data that we could then use to train our model. And an important aspect that's of the design of this experiment that kind of helped to gamify it was that we introduced a trade-off between fast surveillance and personal safety. So I'm going to take a moment to walk through a trial because I think it's really important to understand that, to then understand the results. So in each trial, the participant would be told that the robot was searching the building, and about 4 seconds later, the robot would come back out of this building and either report that there was no danger or that they detected some gunmen, and then accordingly make a recommendation as to whether or not the participant should wear light armor or heavy armor when they surveil that building. And at that point, it's up to the human now to choose whether or not to comply or not comply with that recommendation. If the recommendation was light armor and the human chose to comply with that recommendation, it would take them about 3 seconds to put that armor on. And if they went into the building and there wasn't any danger, no problem, they're all set, and they move on to the next building. If there actually were gunmen and the robot had been wrong, they would incur injury and a 20-second wait period. And so you can see that this would be pretty detrimental to their goal of actually trying to surveil all the buildings very quickly. The alternative option for them would be to wear heavy armor, which takes 7 seconds, so more time up front, but then they don't incur any additional time when they actually surveil the building, regardless of whether there are gunmen there or not. And so it's this sort of these time trade-offs that have been built in that affect the overall trust and workload dynamics that we identified. I also mentioned, again, that the participants interacted with virtual robots that had differing levels of transparency. So let me share those as well. In the low transparency case, this is what each participant would see. They would only be given this report and then the recommendation. In the medium transparency case, we would have that information, but we also threw in this sensor that, again, provided some notion of analysis. And so they would be able to see what the robot sensors detected when they went into that building. And then in the highest transparency case, we went a step further and provided these thermal images that we said the robot had collected when they surveilled the building. And the human would actually, or the participant would have the opportunity to actually look at those themselves to see if, for example, they identified a human form in one of those images that might be representative of there being a gunman present. So we collected data from about 200 participants and then used that data to train the model that I described earlier. And this is a very busy slide, and in the interest of time, I'm not going to go through all of this, but I do want to highlight a few of these transition probability functions just to give you some intuition about how we were able to take data that we collected from this experiment and then again translate it into a quantitative model that we can use to design control policies. So if we look at our trust model, and specifically the emission probability function that we identified, which tells us the likelihood of observing compliance given that the human is in a particular state of trust, what we see is that if the human is in a state of high trust, there's a very high likelihood that they're going to comply with the recommendation. And likewise, if they're in a state of low trust, there's again a very high likelihood that they're going to disagree. And this makes sense and is consistent with what we see in the literature. What's interesting to note is that there is a small but non-zero likelihood that if the human is in a state of high trust, they might still choose to disagree. And this is important because one of the critical things in human-machine interaction is helping humans to discern whether or when to trust automation and when not to trust. And we actually call that trust calibration. If we look at some of the transition probability functions that we identified, and again, these govern the likelihood of the system transitioning from a particular state to a new one, given an action A, or given a set of actions. Here, I'm showing a few of them. Again, we have multiple actions and multiple combinations of them, so there were several of these that we identified. But here we're looking at a case where the recommendation was to wear light armor, and the experience of the human was that the last time the robot gave a recommendation, it was reliable. And so given those actions, we can understand what effect the different transparencies have on the state transitions. So the way to read this would be to look at these three curves and see that the likelihood of the human transitioning from a state of low trust to a state of high trust is highest in this case of this maroon arrow, which is the highest transparency. It's a little bit less when medium transparency is shown to the human and a little bit less when the lowest transparency is shown. Interestingly, it's again the highest transparency that has the highest likelihood of transitioning the human from a state of high trust back down to a state of low trust. And so what this really means, and the takeaway here, is that higher transparency is better for trust calibration, or from a controls perspective, we have the most control authority using high transparency. If we look at our workload model, what we see is that, let me highlight these. For the same scenario, again, in terms of the actions, it is the high transparency, again, in maroon, right here in this 0.3014, that has the highest likelihood of transitioning the human from a state of low workload to a state of high workload. And that makes sense because we know that typically by showing more information to the human, their workload increases. And similarly, the high transparency has the highest likelihood of keeping a human in a state of high workload if they're already there. So again, I'm glossing over a lot of details, but hopefully you're getting a sense for how we can represent behaviors of the human in this framework. So we have this probabilistic model now that allows us to estimate and predict trust and workload. And the next step then is to say, well, could I use this to actually come up with a way to not just show the same transparency to the human, as they interact with this automation from trial to trial, but actually update or change the automation transparency in some adaptive way to that human's trust and workload. And so to do that, we can define a reward function, essentially pose an optimal control problem and solve it. And so when we asked ourselves, what's really the objective here for this human automation team or human robot team? And really it is for the human to surveil all those buildings and to minimize their mission time. And this can be accomplished in two ways. The first would be to help the human to reduce the number of incorrect decisions that they make. But the other one would be to reduce the human's response time. And so these respectively correlate to either calibrating the human's trust, i.e. helping the human to, again, figure out when they can trust the robot, but when they can't or when they shouldn't, and then also just reducing their workload. So we designed a reward function accordingly to accomplish each of these, and then use this weighting factor, zeta, to basically trade off, because these are sort of two levers that we have for accomplishing this overall goal of minimizing mission time. And then we solve our POMDP using a QMDP method and essentially get an optimal control policy. And so what I'm going to do is walk through kind of and emphasize, I think, the key highlight from our control policy that we think is particularly exciting in terms of what we're trying to accomplish with human-machine interaction. So in this case, what I'm showing here is we set zeta to be 0.91. In doing that, we gave high importance to the decision reward and a little bit less importance to the response time reward. In other words, we, again, are really trying to help calibrate the human's trust appropriately to the automation. And if I focus in just on this particular plot right here, what this is showing, kind of a visual representation of the control policy. On the x-axis, I have the likelihood that the human is in a state of high trust. The y-axis is the likelihood that they're in a state of high workload. And what this is saying is that if the robot makes a light armor recommendation, and the robot was correct the last time it made a recommendation, if the human is if our prediction is that they are very likely in a state of high trust, the optimal thing to do is to show them the highest transparency. And essentially what this told us was that, or what the control policy figured out, is that it should essentially say to the human, slow down, hold on. You are so trusting and so compliant that I'm worried that you're going to choose to comply with a light armor recommendation when I'm actually wrong. So let me show you the highest transparency, give you the most information I can so that you can really decide whether or not I'm giving you the right recommendation. When we first saw this, we actually thought we had an error in our control policy, but then realized that this was actually getting at a very tricky issue of overtrust in human-machine interaction, which is super exciting. And if we actually increase zeta to 0.95 to really emphasize the trust calibration, the only change you see is that there's a larger region over which it's optimal to use high transparency. And if we drop zeta and say, well, I do want to calibrate the human's trust, but I really don't want them to incur so much workload, then the optimal thing to do is to never show high transparency and to actually only use medium and low transparency to try to help the human navigate that surveillance. And I realize I'm almost out of time here, so I'm going to go quickly through my last couple slides. The last thing I wanted to mention is that we took this control policy and then actually validated it. So we did a whole nother round of reconnaissance mission, or of human subject experiments using our reconnaissance mission study, where we had a between subjects experiment where individual participants interacted with missions where they were given a fixed transparency, but also missions where the transparency changed from trial to trial in real time based on our control policy. And the takeaway, this is a bit of a busy plot, but what I'm showing here in the middle are 3 different zeta values, so 3 different control policies that we tested. On the left in blue are the total decision rewards. On the right are the response time rewards. And what we're seeing is that using this adaptive automation, we can actually trade off between these 2 mechanisms that enable us to achieve our overall objective. So in other words, by using higher values of zeta and adjusting the transparency in real time, we can in fact improve the ability of the human to discern when they should and shouldn't trust the automation, but that comes at the expense of more response time because we use more high transparency. And so they had to pause basically more frequently to sort of really think about certain scenarios and whether they wanted to trust or not trust the automate, or I should say comply or not comply with the automation. And as we decrease zeta, we can see the trade-off going the other way. The human spends less time deliberating on whether or not they should comply, but then they end up making some incorrect decisions. And then very briefly, I wanted to just touch on some of the more recent stuff that we've done, which is extending this framework to action automation, which I mentioned earlier, and looking at the context of self-driving cars. And this is some ongoing work as well. And then we've also done some work to actually think about how to customize the model that I just described today for different types of humans. So I glossed over some of the details, but we did aggregate all of the data from all 200 people in order to train that POMDP model. And so what that really means is that those transition probabilities that I shared with you, again, may be more accurate for some humans and their own trust and workload dynamics as compared to others. And we've done some more recent work using clustering algorithms to actually identify that there are some dominant trusting behaviors between in the human population. And this is just showing that if we look at the control policy for those two different groups, you can see the optimal thing to do for what we call followers, which are highly compliant individuals, is very different than what would be recommended for people who we called preservers, who were very risk averse in certain situations. And so with that, I want to wrap up and thank everyone for their attention. The work that I shared today, again, I skipped over a lot of details, but it's coming out in detail and just came out in the December issue of the IEEE Control Systems magazine. And I'm happy to and look forward to the questions. So thank you.
Great, Neera, great talk. Really thought-provoking ideas. Awesome. I guess at this point, we can take questions from the audience. And Devesh, do we want to first take questions on Katrina's talk, or do we want to combine the questions?
We can combine the question. I think we had some question for Katrina already in the chat, and she has already answered. So Katrina, if you want, can you just summarize a couple of questions you had in the chat and briefly talk about, or Partha, can you ask your question again? I think that's sure.
I think Katrina started responding to that already, but I was just really curious in her different systems that she's working on the role of sparse data and other challenges in the context of predictive prognostics. So I was very curious, and sparse data is the holy grail in data. So Katrina, thank you. Please go ahead.
Yeah, thank you. Great question. So it's interesting because I think as a risk analyst, my whole career has been sparse data. So it's so interesting when folks are like, well, but how do we handle big data, which has totally different challenges. But in a lot of these systems, I guess, thankfully, the failures are so rare. So we've really had to deal with the fact that, more than 99% of the time in any of these systems, everything is fine. And so we're constantly searching for this needle in a haystack. And so that's where I think the risk assessment the piece came in so naturally, because the PHM handles the big data. And again, I come from the PRA, or the risk assessment background. And looking at that, I was like, we've always had 32 maintenance records or 23 failures in 3 years. So we've, for a long time, looked at how can we use tiny bits of data together with Bayesian models so that we're encoding expert understanding to be able to still use the data. Because our alternative to sparse data was always use no data, which was a no-go. So that's where I think the really exciting thing is that we have all these big data techniques which do things we never thought about, but we never would have been able to say, let's do a predictive big data model on 32 maintenance events. But now, because of thinking about, let's use our risk assessment models, that we've been able to connect those. I'm sorry, did you lose me, or did I lose you all?
No, we can still hear you.
Yeah, we can still
Okay,
hear you.
sorry. It looks like I was losing you. So yeah, we've been able to actually use data that we never, in PHM, never would have been able to use. So I think it's the sparse data piece. It's not as exciting and it's not as certain as big data machine learning models would be, but it's usually, that's the needle we're looking for. That's the piece of hay we're looking for in the haystack, is the piece that failed. And that is such a rare piece of data to have that we can't ignore those 32 near miss maintenance events that we had. So
Katrina, let me just follow up on that. So what is your bias in these kind of analysis? Because you're looking for such a small event. So coming from a turbulence background, we have an event called intermittency in turbulence, which is very hard to really find in the turbulent event. And it's a challenge for people to have a code. You're looking for 1 out of a million event to find. This is what I think you have in this kind of a system.
Right. Yeah, and that's a good question. And we're not quite to the stage. So we know our true positive and our true negative rates. And of course, those are nowhere near the rates that we would like them to be. But that's essentially kind of, I would say, the holy grail. That's where we want to go, is to be able to find those 1 in a million events and to be able to model those. And the challenge is that we don't, we would have to create a massive amount of simulation data to get down to 1 in a million if we did it just in a big data way. But the directions and the indications we have are that we can get there by essentially using smaller amounts of data that we have. But the judgment is a little bit fuzzier than it is in something like a thermodynamics or a turbulence. Is we're not trying to hit an exact value. We're not trying to say, aha, this was the probability. We're trying to get a model that can say this was the best decision given these uncertainties. So it doesn't have to be quite as precise, because it has to really just get us to the point that we're making a good decision in how we respond to that system. But there will of course have to be a layer that both propagates the uncertainty in that information, but also this ability to say we embrace uncertainty. In some ways we say we accept that. There's always uncertainties when we're predicting the future. So we want to propagate, but we're trying to get we're not trying to get as close as some of the more perfectly physically based models are, because all we need to do is say, when the worst day happens, can we get a good engineering, a fast enough, good enough engineering decision to prevent this from escalating?
Thank you, Katrina.
Hey, Katrina, could I ask a question about your stone crusher example? I thought that to be really compelling. How would you productize this kind of capability? Like, how do you envision implementing this? Would it be a part of a real-time embedded system on the device, or would it be something an engineer would have on their smartphone and query occasionally? Could you talk a little bit about practical implementation of the technology?
Absolutely. Yeah, that's a great question. And that's something that I've really had to scratch my head over. And so I would say, it depends. So what's interesting is, and I think it depends on what industry that we're really dealing with in implementing it. And the stone crusher is the industry I know the least. So I started this on the nuclear side. And in the nuclear world, anything directly implemented in the system is almost just impossible, not because of the technology issues, but because of the regulator, and because it would take 30 years to be allowed to use it in a safety critical way. So if it goes forward in that direction, that really gets us to this kind of handheld expert assistance module. But what I'm seeing also is that in the lower consequence industries, like the oil and gas and the mining, that I think there really would be an opportunity to put this directly embedded into the system monitoring and controls. And that requires the right partner who works in that world. But I think that a lot of these systems have so much digital signal monitoring for these components that it's not a stretch to say that if we get this to be fast enough and sufficiently reliable and trustable, that we could actually in the near term actually implement this directly in a system.
That's cool. Thanks.
If I could actually jump in for just a second, Katrina, it's really cool to hear you, hear sort of all of your work and the kinds of things that you would design. Because on the implementation side, what I'm thinking about as I listen to that is the kinds of things that have motivated some of our work in human machine interaction is saying, well, if that system existed and was and that was the intelligent decision aid that was looking at data, making a recommendation or saying, here's maybe what you want to do, how do we design that system so that the human can interpret it under, like, what would be the right transparency for that decision aid to sort of communicate, or in this case, like a reliability assessment, how much information do you actually need to share with the human who's going to have to make an engineering decision? How would you make sure that they're willing to trust that recommendation or that decision? And so I can see some really interesting ways in which on the implementation side, your work sort of translates over to the kinds of things that we think about.
Yeah, I was really excited when I saw your talk, and I was actually Googling some of your work like while you were talking, because I was like, this is like that missing piece, like when you were talking about, again, getting kind of the right level of trust, not too little trust, but also not over trust.
Correct.
I think
Yeah.
that's such a fascinating like insight, and I think that's something that we would have to really consider before ever trying to implement this, because you don't want we don't want safety and reliability to turn into something that's blindly trusted or not even thought about. And so, yeah, everything you were saying about the level of trust and automation, my first thought was, could we actually connect your work to that aspect of mine? And because you were talking about, something that was much more security and human focused, but I think that is a fascinating connection that we should explore between the work.
Yeah, absolutely.
Okay. So there are a few questions for Neera, and before I ask the question, I'll say if you and Katrina can work after this seminar, that will be the real success of this series. So
I am going to follow up with her.
Yes. I had a question about ethics, just because of the last slide which you show, you had a car and you had a person. But generally, when we think about ethics, think about a scenario that on both sides, the decision has to be made. One is an elderly person, one is a young person, and both a human being. You're going to hit one person at that point. How is your control system integrate ethics in the decision-making process?
Sure. So one of the things I guess that's important to note, so we haven't explicitly considered ethics yet. And in the examples that I've provided today, or until now, we've primarily worked on, again, decision automation where the human is always in control. And so there's the ethics are a little bit easier there because I'm not granting control authority to the automation. Even in the self-driving context, I'm not actually touching any of the, So two things. I'm not touching the actual algorithms yet that govern the dynamics of the vehicle. But this is just in terms of, so for example, the motivation in the self-driving context would be, or the scenario there was that the automation or the car is driving itself, but the human can take over at any given time. And we were looking at how can we provide the right level of augmented reality and sort of driving cues to the human to help them decide whether or not they want to take over or not. And so I suppose sort of an ethical question would be, well, if the automation decided that they didn't need to show the cues because based on our model, it seems like that might overwhelm the human at that time, but we had been wrong, et cetera. I don't have a hard answer to that. I certainly am very interested, though, in the ethical questions. And I think that writ large, ethics and automation is extremely important. And actually, if you want to have an offline conversation, we should, because I also have some research interest in that area. But I think that, I don't want to sort of expound on that because the truth is I don't have a good answer. But I agree that it's important, again, not just for these examples, but I think for anything that we're doing in the space of controls and automation as we interact with humans.
Thank you, Neera. Let me just go ahead and read the next question. Or Roxanne, if you want to go ahead and ask your question, then I'll read the next question.
Sure, I can ask my question. So I was curious about how you set up your human study, and your talk was very interesting, by the way. I really enjoyed it. But did you basically have the humans playing a game? Or how did that work? Because you had really cool images from it, and I was just curious where that came from.
Yeah, sure. So we did create all of that ourselves. It wasn't a full-on game. So the human did not actually like go into a building. So it was all static. And it was, so it was really it was a computer-based simulation, if you will, where, all the times where we also, if they got injured, they really had to wait for a full 20 seconds before they would be shown the next building. But all they they just had to imagine that we just said sort of, yep, the robot went into the building, it came back out, and here's what it saw. We do have a driving simulator, so some of the driving work that we're doing now does actually involve a driving simulator that uses sort of game software in the background. And to your other question of, again, how valid is, then this is a big question in this type of research of how valid is what we, learn using these simulated environments to the real world. And there are several sort of papers from the human factors community that do actually show that there is sort of validity, or what we call ecological validity, to simulated studies that can then translate to real world scenarios. The truth is I haven't actually done a study where I had somebody behind, in a real car. And so can I say for sure exactly how well things would translate? I'm not sure, but that is sort of a sort of goal a couple of years from now, where, for example, because of some work that we do at Purdue in the space of automation in trucking, I potentially have access to implementing some of these algorithms for a truck driver driving in an actual platoon on a highway. And so there is a goal to get to a point where we have the ability to test that. But based on our research over the last several years, and we've done other studies beyond the one that I shared today, we've seen a lot of the basic sort of behaviors that we see around trust and workload, again, are pretty aligned with what we've seen in the literature and are pretty consistent. And I think that even though the person may not fear for their life, for example, we're able to induce enough of the sort of trusting and not trusting behaviors. But those are great questions.
No, it's very cool. I'm also wondering if you ever showed an actual human in the heat map. Like, did you have stock images that would make them really out?
My students borrowed a thermal image camera from a heat transfer faculty member and walked around campus and took a bunch of pictures and made their own database and then created all of that. So yeah, the students spent we spent almost a year really getting that experiment right and getting the levels of transparency right to actually distinguish, to actually be able to use them as control knobs. Our first study, actually, we didn't see a big difference between using medium transparency versus high, and actually had to go back to the drawing board and improve the differences between those. So that's one thing I always like to emphasize, that it's really non-trivial to also create some of these experimental platforms.
Well, awesome job. It was very, very, very cool to see.
Thanks.
So Neera, the next question is about the transparency of the levels of transparency. And I think the question is about, should the levels of transparency depend upon decision made at various time scales? And how do you connect the impact of various time scales on these derived control policies?
So I think in the work that, and maybe the person who asked this question can maybe clarify, here time scale was really sort of trial by trial. And so I'm not quite sure what you mean in terms of decisions made at different time scales, because right now they're actually only really making one decision at a time, I guess I would say, on the same time scale.
Yeah, Professor, my name is Murli Krishnan. I'm a PhD student at Purdue, and I asked the question. So yeah, sorry for the confusion.
No, that's okay.
What I wanted to clarify is basically, so in a very complex environment, and I think that's what Dr. Groth, Professor Groth was talking about. And in very complex environments, certain decisions, and when you have various systems working at various dynamics, right? Okay. So the kind of decisions which happen on some systems, like for example, when it's a connected system, on a component level, you might need a much more frequent decision, right? Like you make decisions much more frequently than maybe on a kind of supervisory health level control system where, so that's what I'm trying to talk about. So there might be, on a larger time scale, because you average over so much of the noise, the probabilities might turn out to be in a different way. So that's what I was trying to get at.
Yeah, no, that's a great question. We're doing some work. We've done some work where we looked at, we came up with a somewhat deterministic model for trust evolution before the probabilistic framework that I have now, where we actually defined two states. One was called cumulative trust, which was actually a longer time scale evolution of trust than sort of the more immediate time scale, because you're right that specifically something like trust is affected by often what I just experienced, but also my cumulative experience. And we're doing some work right now with a sponsor where we're explicitly actually running studies where we have folks come in and work, do an experiment on our vehicle sim, and then come back a week later and do it again, so we can start to understand how timescale affects that. So I think ultimately, you're right that the control policy would have to change if we knew that specifically the dynamics that we're interested in, which are what I'm calling the cognitive state dynamics, if those are evolving on multiple timescales, then absolutely we would need a model that accounts for that. And in that case, a POMDP may not be the right framework. And then from there, we would again design a control policy accordingly. So yes, it certainly can get a lot more complex than what we've tackled so far.
Sure. Thank you, Professor. Thank you. Thank you so much.
Thank you.
Here, I had a question about your trust estimator, which I find fascinating. And so the inputs are the system are really the suggested policy.
Yeah.
And transparency also goes in. And really, it seems like transparency is a way of the robot making its case for following a policy. So if that's true, then I guess I wonder, are there other ways you could make your case? Like the robot get louder, or the robot say, I'm right 99% of the time with this. Listen to me. So we thought about other ways that the robot can make its case.
Yeah, so that's a great question. I'm involved with a relatively recent NSF award from the CPS area. That's a collaboration with several other people where we're looking at how we can actually use automation to translate novices to experts. And there, one of the big thrusts is transparency, but moving beyond just visual cues and also thinking about auditory cues and also tactile cues. So to your point, we've not gotten there yet, but you're absolutely right that I think we still lump all those under the umbrella of transparency because it has to do with, again, how the automation is essentially, in my mind, the way I think about it is just communicating to the human. But that can be done in any number of different ways that the human can respond to. And so I think that is going to, and depending on the scenario and how those different types of cues can affect the human, or types of transparency cues can affect the human, it may be more optimal to use a certain type of one in a situation versus another. Because I also would expect that those affect the human's response time differently. And then something that I haven't gone after yet, but I think is really interesting, and that has come up, and that also, Katrina, you or something that you presented made me think of, is the notion of querying. So sometimes, the interactions between the human and machine aren't just, right now we're just thinking about the automation providing information sort of in one direction to the human, but another aspect of improving those interactions would be designing automation that also knows how to ask the right questions of the human at certain times. And perhaps that sort of obtaining specific information from the human strategically can also help to improve sort of the overall performance of the human machine team. And that was something that, again, in the context of like the reliability analysis stuff that Katrina talked about, I thought could make a lot of sense when you're trying to maybe work with the decision aid to actually reach a certain decision. So I'm not sure if that answers your question, but.
Yeah, that's great.
Yeah, can I add on to that? Because I was really excited to see that you had that level of human-machine teamwork also, because one of the things that we're dealing with in like nuclear human reliability is that naively folks are like, okay, let's get rid of human error by getting rid of humans. But the problem is that you have your human operators, and they are the last line of defense. I mean, everyone wants to get rid of the pilot until the plane is doing something horribly wrong because the software is on the fritz. And so I think this is really like a big and important question, is basically like, how do we not replace the humans, but how do we make sure that the now automation based advances are not creating so much, lack of workload for the humans that we expect them to do nothing for 10 years and then suddenly come back and be able to like fix this automated like black box process with 10 seconds and also there's a tsunami coming. So I think like, it's really interesting, especially like seeing your work being rooted in some of the automation and human factors literature that we've used to create these models of reliability for humans. Almost makes me think that like maybe we could connect those human reliability models like back through the kind of work you do and say, well, here's actually where we can find the sweet spot between the human and the automation. Yeah. So we're not just saying, well, here's the way that we can, make the automation replace them or make them trust the automation, but almost like here's where we can finally find where each of them should be, and that we have an actual mathematical and quantitative basis for finally drawing that line. I thought that was a thought I had that was very exciting, kind of based on your work.
Yeah, no, and we should talk more offline, because that's exactly sort of where I think we need to go. And I talked about calibrating trust, and in this work here, we just decided to calibrate trust, but just reduce workload. But in reality, you'd actually want to calibrate workload too, because if the human becomes too over reliant, and because in a lot of situations like processing plants, power plants, where the human operator is maybe primarily sort of in the supervisory role, but then you need them to step in when things go really bad or badly. There's been a lot of work that shows that, again, if they're too disengaged, then and their workload was too low, then they're not able to recover. And so there's actually, in some sense, you don't also want to make things too easy for them, and you don't want to have their workload go down so much that they're able to disengage. And so, and this is kind of coming up in self-driving cars as well. And so I think that this fundamental idea of, what is the right way for humans and machines to interact and share control is super important. And this is sort of, I don't mean to make a selfless plug, but part of what I've been writing about in Forbes for the last couple of months is kind of advocating for this need I think that there are some people who do take this approach of thinking like, we can replace humans, I can design a robot to do anything. And I really deeply feel, both from the ethical standpoint and also technological standpoint, that there is an optimal balance between sort of, maximizing human capability.
I think we
lost her. Yeah.
Well, while we pause, should I answer Wendy's question?
Yes.
She's also, there was a question about what's the targeted audience for the workshop that I mentioned. And that right now it's researcher and faculty and postdoc focused, but of course, highly interested students would be welcome. And the goal is to get academics and researchers from both PRA and PHM in the same room. And it's going to be formatted as a 2.5-day facilitated workshop, where that way we're getting crosstalk between both communities of PRA and PHM in terms of both the researchers and the applications. So we actually have really, so far we've had participants from 5 national labs and several government agencies, and would like to bring in more academic perspective to kind of balance that out. But it's, I think it's an exciting opportunity to get, it's not just an academic workshop, it's really trying to connect into the communities where this is used and to bridge the gaps between those two communities, including, well, I guess the 4 communities, the PHM, the PRA, the academics, and the applications.
Thank you, Katrina. I know it's almost time at the end, so I think Neera can hear her when she hears the recording. So I'll like to go ahead and thank both you and Neera and Katrina for a great talk, and Mark for being there and be the moderator for this session. And I encourage all of you, if you've not seen the website of the Frontier, there are exciting talks. It all gets recorded, so you can share it with your students and other faculty if they're interested to watch this effort. With that, I'd like to thank everyone, and happy Thanksgiving next week and happy weekend.
Yep.
Thank you so much.
Seeing y'all.